Listen up. We're gonna use Python's pip to get all the cool stuff we need for our audio classification models.
We're talking about TensorFlow_IO, TensorFlow_probability, TensorFlow_add-ons, and audio_classification_models.
And don't forget, we're gonna update WANDB too.
These libraries are like the superheroes of audio handling. They'll let us work with our audio data like a pro, train our machine learning models with the best, and even connect with weights and biases to keep track of our experiments and make some fancy visualizations. And to make it all nice and tidy, we're suppressing the output during installation, so it'll be nice and clean.
Long story short, this little code snippet is gonna set us up with everything we need to crush it with audio classification in Python. So, this code we're working with sets up everything we need for our data crunching and machine learning adventures. We've got a whole bunch of Python libraries in here, like Pandas, NumPy, and Seaborn. They're like the building blocks for all the fancy visualizations and number games we're gonna be doing.
We've also got TensorFlow and TensorFlow add-ons, which are the champs when it comes to machine learning.
They're like the brains behind all those predictions and data mining.
Plus, we're using OpenCV for image crunching and WANDB for logging our experiments to the cloud. It's like having a trusty sidekick keeping track of everything. But it's not just about crunching data. We want it to look good too, right? That's where we've set up the font and grid style for Seaborn plots. And TensorFlow? We've told it to keep its chatter to a minimum, so it won't be blabbering in our ear the whole time.
Finally, we've got a whole slew of functions for calculating things like ROCAUCs and confusion matrices. Plus, we've got the tools for tickling TensorFlow with audio data. It's like we're building a Swiss Army knife for machine learning, with everything we need to explore data and make it sing. We've got this cool class called CFG, packed with settings that let us tune our fake speech detector. First off, we've got the basics like experiment name, project name, and a little comment to keep track of what we're working on. And forget about those debug headaches, we've got them covered with the debug mode setting. Now let's dive into the juicy details.
We can play with the sample rate, duration, and even customize the spectrogram settings.
Plus, we've got normalization settings to make sure our data's all nice and consistent. We've also got options for data augmentation, batch size, epochs, and even the loss function. And of course, we can't forget the optimizer and the learning rate scheduler. Each of these babies has a default value and a helpful comment to guide you through the process.
The best part? Different experiments can use different settings.
It's like having a wardrobe of configuration options. And to keep things tidy, our CFG class makes sure all the settings across experiments are consistent. Easy to adjust, simple to import. It's like the perfect recipe for keeping your experiments in check. There, let's talk about how we make sure our results don't go haywire when we're using some fancy Python, NumPy, and TensorFlow tricks. This function is like a guardian of randomness.
It plants seeds for Python, NumPy, and TensorFlow, so they all play by the same rules every time we run our program.
That way we get the same random numbers like clockwork. To make it happen, we just give it a special number called a seed.
It uses that seed to set the random number makers in NumPy, Python's built-in randomizer, TensorFlow, and even the random seed for the operating system. Every time the program runs, it'll churn out the exact same random numbers thanks to these planted seeds. And to let us know it's done its magic, it shouts out seeding finished. Finally, we call this function with a parameter called CFG seed, which is like the master seed for the whole program.
It's the granddaddy of random numbers. So this here code is like a handyman for your TensorFlow operations.
It takes a look around and says, okay, what do we got here?
TPUs or GPUs?
If there's a TPU chillin' in the corner, we'll use a special buddy called TPU cluster resolver to hook it up. Then we'll summon the TPU strategy, which is like a passive scientist to spread the work around on that TPU. But hold your horses. If that TPU is a no-show, we'll check if there are any GPUs kicking it with tfconfig list_logical_devices GPU. If we find some, we'll create a mirrored strategy and use those GPUs to split up the work.
And if neither of those guys are around, we're like, fine, we'll just use the old CPU. So in the end, we give you back a strategy you can use in your TensorFlow code.
It could be the TPU strategy, the mirrored strategy, or just the default strategy if we're stuck with the CPU. And if you're lucky enough to have a TPU, we'll throw in a reference to it for later use. Y'all have fun now.
Alright, let's get this training setup going. We'll call the _configure_device function. This baby will sort out the training device and strategy. It's gonna give us a strategy, a fancy CFG device, and a TPU to play with. Then we're gonna grab the number of replicas for synchronous training from the strategy.
We'll stash it in the _replicas variable. Oh, and here's a little something extra. We'll print out a snazzy string with the number of replicas to the console. That way you can keep an eye on the distributed training setup.
The whole point of this dance to get TensorFlow ready for some serious multi-device training. And we're gonna make sure you know exactly how many replicas you're dealing with. Let's break down how this code works. First, Pandas steps up to the plate to load a CSV file hiding in a specific spot on your computer. It takes the file path and the name of the file, throws them together, and creates a new column dubbed file path in the data frame.
Talk about a handy upgrade.
Next up, it's like a magician waving a wand.
It turns the class _name column into a binary superhero.
It's a battle of good versus evil, with 1 being the sneaky spoof and 0 the real deal. Now, if things get a little lopsided in the data frame, meaning there's more of one class than the other, it swings into action. It randomly grabs 2,500 rows for each target, making sure your data's all nice and balanced. Finally, it proudly announces the number of samples in the data frame, chest puffed out.
And just to prove it's not all talk, it shows you the first 2 rows.
This code's like a secret weapon before you train your machine learning model. It's the behind-the-scenes prep that makes sure your data's ready for the big leagues.
There, let's dive into this Python code. So we got this function called count_data_items that takes a bunch of file names.
Then it's like a detective with a magnifying glass, searching for numbers in the file names using some special code. Something like find me anything that looks like this number.
Ta-da! It grabs the numbers from the strings. And guess what? It does this for each and every file name in the list.
So we end up with a new list that's like a treasure chest filled with numbers. Now it's time for some math magic. The code uses this np.sum to add up all the numbers in the list and gives us the grand total. But hold your horses, it looks like we're missing something.
It's like using a measuring cup without any water. We need to import this NumPy library.
So right at the start of the code, you'll see import NumPy as np. That'll do the trick. We're using the ASV Spoof 2019 dataset for this machine learning pipeline. It's got audio data stored in that fancy TF record format. First off, we grab the Google Cloud Storage GCS path for the dataset using this slick Kaggle datasets trick. Then we go treasure hunting in the GCS path with tf.iog file, globe, looking for files that fit the bill.
Next up, we use the count_data_items function, which, by the way, is defined somewhere else, to count the loot in each training set, validation set, and test set.
We do this by poking around in the TF record files and counting the data items in each one. By the time we're done with this code, you'll have a clear picture of how the data's divvied up and each dataset split. It's like having a treasure map before you set sail on your machine learning adventure. There, let's talk about these 2 cool Python functions in this code. First up, we've got random_int. This function is like a secret agent, taking in 3 pieces of information: the shape of the random numbers we want, the smallest number they can be, and the biggest number they can be.
Then, it whips out a magic wand and uses TensorFlow's random uniform function to conjure up a batch of random integers that fit perfectly within that range.
And guess what?
It makes sure these integers are always the trusty TF32 type. Now meet the second function, random_float.
It's similar to its integer counterpart, but this time it's all about creating random floating point numbers.
It takes in the same three pieces of intel, but instead of using random, uniform, it summons random, uniform with the data type set to float 32. These functions are like superhero sidekicks for TensorFlow, helping you generate random numbers that obey all your rules and fit into any shape you need. Super convenient, right?
There, data enthusiasts. Let's talk about these nifty functions we've got for jazzing up and tittying up your audio data. First up, we've got our Trim Audio Maestro.
This dude's gonna slice off those pesky silent bits at the start and end of your audio, using a fancy schmancy trick called TFIO audio trim. You can even tell it how sensitive you want it to be with the epsilon threshold. Next, we've got the Crop or Pad Rockstar. This one's a bit of a shapeshifter.
If your audio's too short, it'll give it a trim.
But if it's too long, it'll just crop it to size like a pro.
You can also choose how you want it to pad the audio. If it's too short, just in case you're feeling fancy.
Time Shift is another cool cat.
It'll randomly slide your audio back and forth by a certain amount using a trick called TF roll. It's like shaking up a magic potion. And then we've got the Gaussian Noise Wizard. This one sprinkles a bit of random noise into your audio, making it sound like a secret code. You can control how loud the noise is and how often it happens. Finally, we've got the Audio Aug Superhero. This one's a master of disguise, able to apply both time-shifting and Gaussian noise to your audio based on the probabilities you give it. Last but not least, the normalize function is the ultimate cleanup crew.
It'll take your audio and subtract the average value, then divide it by the spread.
Voila! Your audio is ready to party in a machine learning pipeline like it's 1999. We've got two super cool techniques in this code that can pump up your spectrogram data: mix up and cut mix.
First up, we've got the Time Freak Mask function. It's like a ninja that sneaks into your spectrogram and masks out some parts based on these parameters and probabilities. It's got tricks up its sleeves to mask in both time and frequency, using fancy tricks from the TFIO library.
Next, we have the Spec Aug function. It's like a personal trainer for your spectrogram. It uses the Time Freak Mask function to give your spectrogram a workout with specific settings to make it stronger.
Mix-up is another cool cat.
It takes two spectrograms, mixes them up like a cocktail, and even does some fancy transformations to keep it interesting.
It uses a special function called beta distribution to figure out the perfect balance. Cut mix is like a jigsaw puzzle for spectrograms.
It grabs patches from two spectrograms, puts them together, and blends them using this lambda thing sampled from beta distribution.
It's like giving your spectrogram a makeover with little pieces from another one. These mix-up and cut-mix techniques are like steroids for your spectrogram data. They help your machine learning models get smarter and perform better on those awesome audio recordings. We got two cool functions, Audio 2 Spec and Spec 2 IMG. Audio 2 Spec takes an audio signal and turns it into a spectrogram. It's like a visual representation of what your song is saying.
It crunches the numbers using some fancy settings, like how big the window should be and how far apart the jumps should be.
Then, it cooks up a spectrogram, converts it to mel scale, chops it up on a logarithmic scale, making the loud bit seem even louder, and shapes it up nice before sending it back. Now Spec 2 IMG is a different beast. It takes that spectrogram, which is like a flat image, and turns it into a proper image with all the right dimensions. It adds an extra layer, like the number of channels in a color TV, usually just one. But get this, if the spectrogram has more than one channel, it clones it across all the channel axes using TF-tile.
It's like taking multiple copies of the same image and stacking them on top of each other.
So there you have it. Audio 2 Spec makes spectrograms from audio, and Spec 2 IMG transforms those spectrograms into images ready for action. Let's start with the TF record, shall we?
It's got this example in it. We're going to grab that audio right out of the WAV file and turn it into numbers we can understand. And guess what?
This function ain't shy about what it's got inside. It lists everything: the audio, the ID, even the speaker and system IDs.
It even knows how long the audio is and what the target label is. Now let's use this function to pick out one of those examples from the TF record. We'll turn that audio into numbers using our trusty decode_audio helper. And don't forget the label, we'll make sure it's a float 32, because that's how we roll. Oh, and here's a little trick. We're going to trim off any extra noise at the beginning and end of the audio.
But wait, there's more.
We'll crop it or pad it if it's not the right length.
That way, it's all nice and even. And then the magic happens.
We've got this audio aug function that can transform the audio in all sorts of ways. It's like a sound effects factory. We'll also turn that audio into a spectrogram, which is like a cool visual representation of the sound. And just for kicks, we'll use spec aug to enhance it a little bit.
Now let's wrap it all up into an image format.
We'll clip it to a certain range and reshape it. And boom!
We've got our processed audio data ready to go. Oh, and one last thing. You can choose whether you want labels and IDs included or not. It's all up to you, baby. There, check this out. So, this function, get_dataset, it's the boss when it comes to getting your TensorFlow data pipeline up and running.
It's like a Swiss Army knife for data processing, with all these fancy knobs and dials.
First off, it grabs your TF records files like a pro. Then it's all about speed and efficiency.
It caches the data, so you don't have to keep loading it over and over, and it can even repeat it if you're feeling the training vibes.
Now let's talk mixing and matching. If you want your data all nice and shuffled, just give it a nod, and it'll do the trick.
It'll also parse your data into nice, neat rows, complete with IDs and labels, and throw in some extra zest with data augmentation options if you're feeling adventurous.
Then it's time for the group hug. It batches the data into cozy little groups.
And if you're into mix-up or cut mix, it's got your back.
Plus, it'll prefetch the data to keep things moving at lightning speed. Finally, it spits out a dataset that's all configured and ready to rock your training or evaluation models.
It's like the perfect symphony of data preparation, making sure your ML tasks like deep learning with TensorFlow are smooth as butter. So this nifty code comes with a bunch of functions to make your life easier for analyzing your machine learning models. First off, you've got !plot_confusion_matrix .
It's like a magic wand that takes in a confusion matrix and a list of classes.
Then, bam! It plots the confusion matrix all color-coded and labeled for you. You can even tell it to normalize the matrix if you want to get fancy. Next up, we have !plot_history . This one's like a cheerleader for your model's performance.
It plots the F1_ score and loss values over epochs.
It'll point out the highest F1_ score and lowest loss too, and it saves it all in a neat little plot called !history_plot.png . And last but not least, there's !display_batch . This one lets you peek at a batch of data.
It'll show you the images with their labels, all nicely arranged in a grid. It uses the batch data and the number of rows and columns you tell it to use.
These functions are like your trusty sidekicks when you're working with machine learning models. They help you see how well your models are performing and make analysis a breeze. There, let's take a peek at this code snippet that's like a personal shopper for your data. With these first two file names from our train_filenames list, it's like telling your shopper to grab just those two items. Then it creates a dataset, but without any fancy extras like fancy wrapping paper. Next, it's like going to the checkout counter and grabbing a basket of 20 items. That's our batch size. We're taking those images and targets and putting them in our basket. Now let's see what we've got.
We print out the shapes and data types of the images and targets. It's like checking the ingredients on a food label. But wait, there's more.
We can even use a display_batch superpower to show off a batch of images in a cool grid layout, 3 rows by 3 columns. It's like having a little photo album of our dataset right before our eyes. So this code is basically saying, hey, let's get a few items from the training dataset, see what we've got, and then take a peek at a couple to see what they look like. It's like doing a quick inventory and browsing before you commit to the whole dataset.
Check this out. This code snippet's got the lowdown on processing a dataset.
It's like the boss parsing file names to get a batch of images and their targets for some serious number crunching. Hold on, here's the nitty-gritty. It grabs the dataset from the first 2 training files, throws in some jazzy real-time data augmentation, and keeps it fresh, no caching here.
Then it's like, hold your horses, amigo.
The take one method reins it into just one batch, which we unpack like a piñata into 2 variables. "imgs" images and "tars" targets.
Wait for it.
The code dishes out the inside scoop on the target and image shapes like a pro, and even lets you know what type of data you're dealing with. Finally, it's time for the big reveal.
The "display_batch" function steps into the spotlight and whips up a rad visual representation of the batch data.
It's like an art gallery but with data instead of paintings.
So there you have it, folks.
This code snippet shows you how to check out a slice of data from a dataset, all ready for model training or whatever your analytical heart desires. So this code's got a nifty function called get_metrics. That'll whip up a whole bunch of metrics for you to check out how your binary classification models are doing. You've got your basics, like binary accuracy, to tell you how many of your predictions were spot on. F1 score for that balanced view of precision and recall. And precision to show you how often your model was right when it predicted something.
Recall will help you see how often your model found all the true positives it could. But wait, there's more.
We're not stopping at just these few metrics.
We've got a whole range of them, so you can really dig into your model's performance.
During training and testing, this function will hand you a nice little list of these metric objects.
They'll tell you exactly how well your model is doing at different things, like being accurate, catching those true positives, and avoiding false ones. It's like having your own little performance report card. As your model learns and makes predictions, these metrics will change, giving you a real-time snapshot of how it's doing. This code has a nifty function called get_LR_callback.
It's like a secret weapon for cooking up learning rate schedules for your neural network training.
You can tell it which way you like your learning rate to dance, exponential, step, or cosine.
It also needs to know the size of your batches, how many epochs you want to groove to, and if you want to see a graph of the party.
In the last epoch, the learning rate gets a makeover.
It can drop like an exponential curve, take steps down, or follow a cosine pattern, depending on how you like your music. We're talking about a shift from 5e-5 to 5e4, so it's a big deal.
With this code, your learning rate will bounce to the beat of your schedule.
If you want to see a visual jam, just turn on the plot flag and you got a sweet graph.
In the end, you get a learning rate scheduler callback that's ready to rock with TensorFlow Keras. So pick your mode, and let's experiment with learning rate strategies.
This code is like a Swiss Army knife for optimizing your neural network training. Listen up. We're going to dive into this code here.
We're calling the get_LR_callbacks function with a few fancy options.
First up, we've got mode set to whatever's stored in cfg.lr_schedule. That's like the roadmap for our learning rate. Then we've got epochs set to 30, so we're going to train for that many rounds. And lastly, plot is set to true, which means we'll get a fancy graph showing how the learning rate changes over time. Now this function is going to spit out a learning rate callback object.
That's like our secret weapon for guiding the learning rate during training.
Epochs tells us how many times we're going to train through the data, and mode decides what kind of schedule we're going to use to adjust the learning rate. And because we asked for it, we'll get a sweet graph that shows us exactly how the learning rate changes as we train.
Isn't that cool? This callback object is our trusty sidekick, helping us figure out the best learning rate strategy for our model. There, let's dive into this conformer encoder, shall we?
This encoder's like a secret weapon for audio classification tasks.
It's like a deep learning model that's tailor-made for understanding the sounds you throw at it.
But here's the cool part. You can tweak it to your heart's desire.
Want to change the shape of the input? No problem. How about the number of classes? Go ahead and play around. Even the final activation function is up for grabs.
Oh, and don't forget the pre-training option.
If you want to give your encoder a head start, just set it to true. It'll load up some pre-trained weights and hit the ground running. To get started, you just need to set up the input layer with the shape you want. Then our trusty encoder module takes over, using its conformer magic to create this awesome encoder.
If you're feeling fancy, you can even add some extra layers, like a global average pooling layer to squeeze down the output size. And of course you can throw in some dense layers for good measure. Finally, we wrap it all up in a neat little Keras model object that represents your whole model. It's like the masterpiece you've created with all the bells and whistles you've chosen. So there you have it, a flexible, customizable conformer encoder that's ready to rock your audio classification projects. It's like having a superpower to understand the language of sound.
Alright, so here's the lowdown.
When you want to train your model, you just call this magical Python function called _get_model. It'll whip up a neural network for you, nice and fast.
It takes a couple of things from the config file, a fancy name and a loss function.
Inside the function, we'll make a conformer model, all fancy like with the right input shape and ready to do its thing. Then we pick an optimizer like Atom or Atom W, depending on what you specify in the config. If you throw something wonky in there, we'll yell at you.
Then boom!
We compile the model with the optimizer, loss function, steps per go around, and anything else. The _get_metrics function tells us to.
And voila, you've got yourself a shiny compiled neural network.
In a nutshell, this code makes it easy to build and train your neural networks with all the bells and whistles you need, all thanks to the config file. After we've got a model from somewhere, like with this _get_model function, we can take a peek at its blueprint using the !summary method. It's like looking under the hood of a car to see all the different parts. This !summary thing gives us a nice little breakdown of each layer in the model, like what each one does and how big it is.
Plus, it tells us how many adjustable knobs there are to tweak during training.
It's a super handy tool to get a quick grasp of how a model is put together and how complicated it is. So let me break down this code for you.
It's like the bouncer at a secret party. It checks if you have the right password, which in this case is the configuration flag CFG_WANDB.
If it's set to true, it's like saying, "Party on, dude,"
and tries to get you into WAND using a special key it grabs from Kaggle. If you're not on the guest list, it's sorry, not this time.
But if you're in, it initializes a whole new party with WANDB, using the WANDB_init function.
It puts together a random secret ID with the configuration details, leaving out any double underscore stuff. Then it calls WANDBinit to start the party. Now the party gets tailored to your vibes based on the configuration.
It gives the party a name, a specific project, and sets whether you're going anonymous or not.
On top of that, it loads in some extra WANDB setup.
Think of it like this. If you have that Kaggle API key, it's like having the ultimate party pass. You can log into WANDB and start your own personal party there. Otherwise, it'll be a public bash.
Check this out. We've got this cool code here that uses TensorFlow and Keras to train a deep learning model like a pro. First up, we tell it where our training, validation, and test files are hiding. But hold your horses.
We're only looking at a few selected ones, because we're like quality over quantity, man.
We also give it a good shuffle to mix things up, and then we count how many samples it's got in each set, like a boss. Now let's talk about the nitty-gritty.
We set up the batch size and how many steps it'll take per epoch, because that's important stuff. Next, we build our deep learning model, and if we need to, we use a fancy distributed strategy to split the work between multiple accelerators, like a total baller. We also add some callbacks to our model training, like checkpointing our progress and adjusting the learning rate on the fly. Plus, we're keeping track of all the details, like the image size and batch size, so we don't miss a beat. Now it's time to train our model. We're going to run through a bunch of epochs and we're logging all the training history so we can see how it's doing. When we're done, we'll load the best weights back into the model like a champ.
And if we're feeling extra fancy, we'll plot the training history and even log it to an online dashboard using WAND so we can track our progress like a pro. Boom!
Training complete and we're ready to rock. There, let's dig into this code snippet.
First off, we're giving our machine learning model a good once-over to see how it's performing. We've got the best weights loaded in from a file, and we're spitting out the evaluation results.
Next up, we're bringing in weights and biases, WANDB for short, to help us keep track of things. We're going to figure out which epoch is the golden child based on the validation F1 score, and we'll jot down the validation and test results. Then we're unleashing our model on the test dataset and making some predictions. We'll process those predictions and pull out the IDs and labels from the test dataset.
Finally, we're building a confusion matrix using the test labels and predictions. To make it easier to understand, we're plotting the confusion matrix with the classes real and fake clearly labeled.
Yo, check this out. We got this Python code trying to get rid of a directory called WANDB, like it's a total nuisance. It's using the rm command through something called the shuttle module. But here's the thing, the shuttle module is like a helper for working with files and stuff, not for running commands like rm directly.
So the code is like syntax error, dude.
And then there's this try except block that's like a bodyguard catching any errors that could pop up.
But even if there's an error, the code just keeps on trucking. I'm guessing this code is trying to say goodbye to the WANDB directory as part of some cleanup thing it's doing. But it's going about it the wrong way.